Hello, calculus fans. All right, let's try another derivative. We're going to compute the derivative of x to the 5/6 times the cube root of x squared plus 1 all over 2 minus 5x raised to the 7th power. What a mess. Now, you could differentiate this by using a lot of our various rules, things like the quotient rule, the product rule, the chain rule, the power rule. If you put all those together, you could compute the derivative of this and it would work out fine. It would be messy, but you could do it. Now instead, I'd like to introduce a new technique. And this new technique is known as logarithmic differentiation. It's a useful technique when you're differentiating a function which is a product and maybe a quotient of powers and roots. That's exactly what we have here. We just have a lot of roots and powers. We're multiplying things and dividing things. All right, so let's go through the steps of logarithmic differentiations. The first thing we want to do is write out y equals whatever function that we want to differentiate. And then what we're going to do is take the logarithm of both sides. Now this is just a little bit of preliminary work so that we can more easily take the derivative. We'll see where this is going to go. All right, so we take the log of both sides and we get this expression here. So on the left-hand side we get log of y. On the right-hand side we get log of that big expression. Now we're going to try to simplify. And we're going to use all of these properties of logarithms that we talked about previously to simplify this. We've got products, we've got quotients, we've got powers, so we can use those properties to simplify. So let's see what we have after simplification. That product in the numerator turns into log of x to the 5/6 plus log of the cube root of x squared minus 1. But then we have to subtract off the log of what's in the denominator. Now we're going to keep going with our logarithm properties. You see a bunch of exponents there. They can be moved out in front of these logarithms. And so if we move those powers out in front, then we get something like this. Notice, we have not done any calculus yet. This is just a little bit of algebra to manipulate these expressions. We've taken the log of both sides and then used a bunch of logarithm properties to simplify this. So that's the first step in logarithmic differentiation. Okay, let's talk about the second step in logarithmic differentiation. And that's to go and use implicit differentiation on what we have. So we have log of y is equal to this, and we're going to differentiate implicitly now. So here's what happens after we take a derivative. On the left-hand side, when we differentiate log of y, we end up with 1 over y times y prime. So we get 1 over y because that's the derivative of the log function. But we also have to have a y prime in there because we're differentiating with respect to x. Now on the right-hand side, all of these simplified expressions allow us to much more easily take a derivative. So for instance, 5/6 log x, that turns into 5 over 6x because the derivative of log x is just 1 over x. Okay, now let's look at the second one a little more carefully. If we're going to do the derivative of 1/3 log of x squared plus 1, okay, so remember what the derivative of log of x squared plus 1 is. It's 1 over x squared plus 1. But then we also have to multiply by the derivative of the inside, and that's where you see the 2x. Now you notice I didn't do any intermediate steps. I went directly from this to its derivative. And I think that it's about time that we started getting used to that kind of thing, to do our chain rule in one step rather than writing out an intermediate step. Well, you'll be able to see the same kind of thing in the next piece, where when we differentiate this, we should get this expression. So you might ask, where's that 35 coming from? Well, to start with, we're differentiating a log function, and the derivative of that log function is 1 over that thing. And then we have to multiply by the derivative of the inside. Now let's look carefully at what the inside is. It's 2 minus 5x. So what happens when you differentiate 2 minus 5x? You'll get a negative 5, and that negative 5 combines with this negative 7 to get 35. Now, if you feel the need to write out some intermediate steps, by all means, you should go ahead and do that. But I do think it's worthwhile to be able to skip those intermediate steps of the chain rule and move directly to your final expression. So now let's think about what we've got here. We've computed a derivative. Our goal is to solve for y prime. So let's get that y prime by itself on one side of the equation. We can accomplish that by multiplying both sides by y. That will isolate the y prime on the left-hand side. Okay, so when we multiply by y, we'll get this expression. Now, ordinarily in implicit differentiation, we quit here. But there is one thing that we can do to finish our this derivative, and that is we can replace the y with the original value of y that we had at the beginning of the problem. So let's see what happens when we do that. So all we did here is replace this y with the original y, leaving everything else intact. Now, that's it. Let's not do any simplification of what's here. We have some gigantic mess, that's true, but why bother? We're not going to do anything more with it. This is our final answer. We've computed y prime. Okay, that's all for now.